The building blocks of efficient programming. Data structures in action. In the world of algorithms and software development, data structures form the foundation upon which efficient solutions are built. They determine how data is stored, accessed, and manipulated within computer programs. Understanding different types of data structures enables developers to choose the most appropriate one for their specific use case, leading to optimized performance and maintainable codebases. Fundamental concepts in data structure design. Data structures define ways to organize and manage collections of data efficiently. Common structures include arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Each structure has its own strengths and weaknesses depending on operations required, such as insertion, deletion, search, and traversal efficiency. Arrays provide constant time access but fixed size limitations that can lead to memory wastage or reallocation overheads. Linked lists allow dynamic resizing through pointers but require extra space for storing node references. Selecting optimal data structures for algorithmic challenges. The choice between linear versus nonlinear data structures often depends on problem requirements. For example, when frequent insertions/deletions at arbitrary positions are needed, linked lists may outperform arrays. For applications requiring fast lookup times without ordering constraints, hash tables provide average case O(1) complexity for these operations. Evaluating time-space trade-offs. Designers frequently face trade-offs where improving one aspect might compromise another. A tree data structure offers faster prefix searches than binary search trees but consumes more memory. This balance becomes critical during competitive programming contests where both time and memory constraints matter significantly. Implementing classic data structures in code. Coding implementations vary across languages, though core principles remain consistent. In Python, list comprehensions enable array-like behavior while dictionaries mimic hash table functionality. When implementing custom structures like stacks or queues from scratch, it's essential to understand underlying mechanisms rather than relying solely on language-specific features. Advanced applications in modern software systems. Complex systems leverage combinations of data structures to handle sophisticated tasks. Databases employ B-trees for indexing, while graph databases utilize adjacency matrices or edge lists for storage. Real-time applications benefit from priority queues implemented using heaps to process events based on urgency levels rather than arrival order. Benchmarking performance characteristics. To evaluate effectiveness, we analyze time complexity metrics under various scenarios. Big O notation helps categorize algorithms by worst-case performance expectations. Space complexity considerations become crucial for embedded systems where memory allocation needs strict optimization without compromising speed requirements. Common pitfalls and best practices. Misunderstanding structural characteristics leads to inefficient solutions. Using an unsorted array for repeated lookups instead of a hash table results in O(n) operation costs repeatedly. Properly selecting iteration methods ensures optimal traversal patterns. Breadth-first search works best with queue structures, whereas depth-first requires stack-based approaches. Evolution of data structures over time. Historical developments show continuous refinement of existing concepts alongside new inventions. Skip lists introduced probabilistic techniques for maintaining sorted sequences with logarithmic expected time complexities. Modern research explores novel structures like Bloom filters for approximate membership queries and segment trees for range query optimizations in computational geometry problems. Conclusion. Data structures serve as fundamental tools shaping modern computing landscapes by enabling efficient information management and manipulation. Mastering diverse implementation strategies empowers developers to tackle complex challenges effectively through informed design choices and rigorous analysis techniques.